Welcome back, Organic Chemistry 2. This time we're with Chapter 13. Chapter 13 is relatively short. In theory, it should contain 4 different functional groups: ethers, epoxides, thiols, and sulfides. But as you can see, the thiols and sulfides are in blue, meaning that we are not going to be covering those 2 functional groups. Okay, so thiols and sulfides, those are sulfur-containing functional groups that are very important in organic chemistry. In the sense that they are very good nucleophiles. Uh, they are they are part of, I mean, some type of defensive system of some animals, for example, skunks, right? So they work with sulfites and thiols in a way to protect themselves, right, from any type of predators that they might be exposed to. So and they are also part of, a lot of industries for example, in the pharmaceutical industry, proteins, peptides, amino acids in general. They have also an amino acid called cysteine. Cysteine contains sulfur. Hair industry, dyes, all that is based on sulfur chemistry. So that's why they have a very strong smell. I don't know if you any walk by, a salon, right? That they do a straighten, they make curly hair, or they make, straighten the hair. It has a particular smell. That smell is from thiols and sulfide. Those are products that they use for cosmetics, right? Normally for hair products. Okay, but in our case, we're going to be covering ethers and epoxide. Ethers, they are very, normally they're associated with solvents and anesthesia, right? So ether, right? So it's, for example, lidocaine, benzocaine, those type of compounds. They are believed that, I mean, they're known to have a very good type of effect on the response of the muscle responses, um, the nerve system, right? So it prevents the transmission of sensations of pain to the brain. So that's why these guys are used for that purpose. Epoxides, where do we see epoxides? Normally we see epoxide in resins, industry, industrial applications, tapes. All that is based on epoxides. Okay, epoxide, we also find it in dental products. So epoxides, that glue that they use whenever they put like a cover or a filling, right? So those are all epoxides that are activated by UV light. So that type of glue is made of epoxide. So it's a really broad, application for these 2 functional groups, other than solvents. Normally for ether, we think that is solvent, diethyl ether. True, diethyl ether is a solvent, but ether is really a functional group that, that is hiding more things inside. Ether is right here at the top, right? So the functional group is right here. So you have an oxygen that has 2 R groups. Those 2 R groups, R group is conventionally used as any substituent, right? It can be aliphatic, can be aromatic, can be a cyclic compound, and it doesn't really matter what is the identity of that R. All what matters is that the oxygen is attached to 2 carbons. So those carbons can be in a ring, in a benzene, or an open chain, doesn't really matter. Here, there is one of them. So we have melatonin, right? So here has an ether on this side. It also has an amide. Amide is right here, has an amine, has a benzene ring. We have propanolol, right, which is also another type of uh, pharmaceutical product. So there is actually like there's some CSI, crime, crime investigations are based on propanolol, because depending on the dose, propanolol can also cause death. Right? But it has an ether inside. Vitamin E has an ether inside. It's a cyclohexane, right? Cyclohexane-like type of compound, and the oxygen is right there. So morphine is another, is used for drugs, as a pain, is a very powerful painkiller, right? So also an ether. It has a bicyclic compound right here, has nitrogen, amine, phenol. This is a phenol. This one will be an alcohol. Uh, tamoxifen, and then there are many other drugs that they have, the ether functional group inside. Something to say about the characteristics of ether: they are solvents. Because of their low polarity, they have like a relatively low boiling point. In this case, these guys might be solids. these are all solids mostly because of their size, right? The weight, the molecular weight is really high. So definitely we are not really going to expect this guy, vitamin E, for example, to be a liquid. No, it's too heavy. So, the bigger the molecule, of course, the heavier it is, the more the options to be a solid. But if we're talking about that very small, let's say like two carbons on each side of the ether, of course, they're going to be a liquid. And what are they liquid with low boiling point? They have a low boiling point because the ether does not have such a high dipole moment. Okay, there is a dipole moment that gives some small polarity, but that polarity is not that big enough, right, to give a relatively moderate, boiling point. Okay, so ethers are known to have relatively low boiling point. What is relatively low boiling point? The relatively low boiling point would be like in the 30s, 20, right? Even at room temperature might be in a hot day, it might be already evaporating pretty quickly. It's a very volatile, volatile functional group. So for example, if you have a beaker with ether, after 5 minutes, most likely all the ether is going to be gone because they have a very, very low boiling point. Okay. They're also very flammable. Since they evaporate, they have a flash point, a very low flash point. The flash point is the temperature at which a liquid, a volatile liquid, might ignite, just by evaporation, right? So for example, next to me, I have an ether, right? Diethyl ether, let's say, and that diethyl ether, I don't really have to put like a, fire inside. If I'm holding, let's say like 1 foot away, lighter, if I decide to ignite it, yeah, the vapors of the ether will cause, the ignition of the liquid. So it will start, burning. So that's called a flash point. Okay, flash point is different from boiling point. Boiling point is the temperature at which a liquid boils. Goes from the solid phase to the gas phase. In the case, the flash point is the temperature at which a particular volatile flammable liquid can produce flames. Okay, so that's the flash point. Okay, so here are an example of ether. Something about the naming, right? So in the case of naming, we use a common name, a common way how to name ethers. You see both sides of the ether, and those are relatively small ethers, right? So here you call it ethyl methyl ether. You go by alphabet, that's why ethyl is named first, and then M, right? Ethyl methyl ether. Here is terbutyl methyl ether. Say, Professor, why is terbutyl if it starts with a T? Because the prefix tert does not affect the naming. It's one of the prefixes that is kind of like invisible. Okay, so really what counts here is the B as from butyl. So butyl is what counts, methyl ether. Diethyl ether, same thing. So here is ethyl. Now you group them and then call them diethyl ether. Okay, so it's only 2 branches. So you guys will always name the ether based on these 2 substituents. Another one is considering the alkoxy substituent. So you have like this type of ether, for example, 2 carbon chain here, 2 carbons, and then 5 carbons. Of course, I'm going to consider this guy as my substituent because it's smaller. The smaller side chain will be the substituent or of the longer side chain. So in this case, I will call it ethoxypentane. Okay, so let's do a couple more to see what will be the name for this. Okay, this ether, this group is called isopropyl. So in the case of isopropyl, so I will call it diisopropyl ether. Okay, so that would be the name, right? Diisopropyl ether. Professor, what about the iso? Does the iso count for alphabet? Yes, the iso does count for alphabet. So for example, if I have here, so this side chain is called isopropyl, and this one is ethyl. The I does count. Okay, iso and cyclo, they both count. Okay, what about third? Third does not count. Sec does not count. And there's another prefix which is called neo. The neo does not count either. Okay, so you was a neopropyl, neopentyl. It could be, but we don't use, they are not considered for the alphabet. Iso and cyclo is the only one that they count. Okay, so in this case, the iso counts. So the name would be, ethyl isopropyl ether. Okay. What about in this case if I want to name it as a prefix, right? In this case, no. The diisopropyl, because it's a repeat. This one, this ether is unsymmetrical, is not symmetrical. Which side is shorter? So the shorter side would be the ethyl. So I would call it ethoxy isopropane. Okay? Because the ethoxy would be the substituent, which is this side. Let me circle it, right? That one would be, sorry, the whole thing. The whole thing will be the substituent is ethoxy. This is the ethoxy, the whole thing. I'm going to shade it. The whole thing will be ethoxy, and this one will be isopropane, right? So that would be the name for that compound, right? Good. So let's continue with the slides. Right, so about the physical properties of the ethers, right? So water has a bond angle of 105 degrees, more or less. Methanol is an sp3 hybridization, is also very close to 109. In the case of water, right, so it's a little bit smaller, and that's really an explanation. It can be on the test or the quiz exams. Why is it smaller? It's here the oxygen is right? Here the oxygen, right, has a sp3 hybridization. Why is this bond angle, right? This is smaller because remember that you have two lone pairs of electrons. These two lone pairs of electrons will create repulsion to each other. So how can they prevent the repulsion of the two lone pairs, right? These two pairs of electrons. So to decrease the repulsion, so they have to be more spread out, right? The two lone pairs have to be more separated. To separate them, they have to sacrifice this bond angle. So this bond angle gets sacrificed since they are hydrogens. Remember, hydrogen is the smallest element in the periodic table. Of course, they will give room to that squeeze. So that's why it gets decreased to 105. It's just in the benefit of the electron-electron repulsion from the lone pairs. What happens in methanol? So methanol, why does that not happen? Now you don't have two hydrogens. Now you have a methyl. Methyl does have a considerable volume. So since methanol has the methyl, these lone pairs of electrons, they want to separate, they want to reduce repulsion. Yeah, to do that, they have to squeeze this other angle. But the methyl will say, no, I'm right here. I need a space. I cannot just give up, right? Give up on that space because I'm bulky. I have a volume, so I need a space. So from, I think it's 109.5, maybe gets decreases slightly to 109. So there's a small decrease for that, but it's really in compensation of the, just for the electron repulsion. What happened in dimethyl ether and ether in general? That actually happens the opposite. The lone pairs of electrons, they do not really, they are not they are not hurt. So in this case, actually the steric hindrance, right, is a term that we use a lot in organic chemistry 1, steric hindrance. Right? In the case of steric hindrance, you guys have the oxygen with the two lone pairs of electrons, and you might have an ethyl and a methyl. And of course, this ethyl and methyl, they have their own atoms, they have their own electrons, they have their own protons. And of course, there is a type of collision here. That presence, right, that neighborhood, right, between the two groups creates that the angle in this case actually opens. Right? Of course, if you have a cyclohexyl, or if you have a benzene ring, right, that situation gets worse because it's a bulkier group, it needs more room. So in that case, the electrons have to be sacrificed. So the electrons will not have other choice, right? If there is room available, of course, the electrons will use it. But if the if the bulky, right, the bulky substituents of the ether are the ones that are really having a hard time to exist, then they will definitely take on that space, right? So that's why in the case of the ethers, right, that angle goes from 109 to 112. And it depends. I mean, is that really a square angle like 112 is a fixed angle? No, it depends on how bulky it is. So here we're talking about, let's say, like 2 methyls. Maybe if I have 2 terbutyls, of course, maybe we might go to 112, 113, 114 degrees, right? But it depends on how bulky it is. So this side is this part of the slide is telling you about the physical property, which is called polarity of the ethers and alcohol. Some of you might be wondering, is ether fully insoluble in water? No, there is a very small portion of ether that goes into water. It's able to dissolve. Why is that? Because ether is a very good hydrogen bond acceptor. Ether has oxygen with electrons, so they are able to form hydrogen bonds. So a very tiny amount, let's say like 1%, or maybe a little bit less than 1% of the ether will be soluble in water. What about alcohol? Maybe in alcohol might be a little bit more soluble, but the interaction is also by hydrogen bonding. Remember that the non-polarity of the ether really depends on the R groups. The longer these R groups are, of course, the less soluble in water it will be. Okay, so for example, you tell me, oh, dimethyl ether. Dimethyl ether is a very small ether. So most likely the dimethyl ether could be our most soluble ether that we have in nature. Okay. Why? Because the hydrophobic part, right? The 2 parts of the that can contribute to hydrophobicity are very short. So it's only 2 methyls. So the most predominant element will be oxygen, which is electronegative and is able to form hydrogen bonds with water. So this one might be a little bit more soluble in water. But by telling you soluble in water, I'm not saying like, oh, completely soluble. No, it's not about full solubility. We're saying the very small solubility. Okay. But it is able to form hydrogen bonds. You can see here on this side, right, that an alcohol, it doesn't say the density of the alcohol, but it gives you a good solubility. So if you mix ether in alcohol, let's say ethanol or propanol, isopropanol, rubbing alcohol, it should dissolve. Okay. Why? Because alcohols are different. Alcohols are not fully polar. They have some an alkyl group here, right? An R, a chain here or a ring that might interact, right, positively with the ether side chains as well. But can they form hydrogen bonds? Yes, they can form hydrogen bonds. Ethanol, here's a good comparison like of the 3 functional groups, well, alkanes, we can call them functional groups, that they compare the relative boiling points. Ethanol, 78 degrees. Dimethyl ether is actually a gas at room temperature. Dimethyl ether has a minus 25 Celsius degrees boiling point. That means that it's not a liquid. You need to be a minus 25 to be a liquid. And propane, which is the domestic gas, right? Domestic gas minus 42. The idea of this slide is like to explain why is this one, right? Has a higher boiling point, followed by the dimethyl ether and the propane, if they have about the same molar mass. So it's not about how bulky it is, how many branches they have. It's only about the intermolecular forces. The molecular weight is the same, but this one is a gas, this one is also a gas, and this is a liquid with a relatively high boiling point. So why is the reason? Well, the reason is because ethanol is able to form and accept, right? It's a donor and an acceptor of hydrogen bonds. Dimethyl ether, no. Dimethyl ether is only a hydrogen bond acceptor, so it's not going to form hydrogen bonding with itself, right? So I think that that's very important to really explain that part, okay? So in the case of water, water is a hydrogen bond donor and also a hydrogen bond acceptor. So in this case, right, as we were explaining, let me see, let me find it, okay. Okay, this one is a hydrogen bond acceptor. It will accept the hydrogen bond. And this one will be the donor. That's the donor, that's the acceptor. Okay. In the case of water and alcohol, let's say methanol. Methanol is a hydrogen bond donor. Sorry, donor here. And it's also a hydrogen bond acceptor. It can do both. So that's why between 2 methanols, it's a perfect interaction because it will interact on both ways. Donor acceptor, donor acceptor. Okay? It interacts, it has both components of the hydrogen bond at the same time. In the case of ether, no. Ether only has the hydrogen bond acceptor. These are the acceptors. So you put dimethyl ether with another dimethyl ether, so there will be no forces because they are both acceptors. They are both acceptors. If they were acceptors, no, you need a donor to form a hydrogen bond. So what happens with the molecule? The molecule will have a very low boiling point. Why? Because there is no hydrogen bond here. Dipole, yeah, there will be a very small dipole, right? Formed by the, by the dipole moment that you have between the CO, right? But that's all. And it's a carbon oxygen. So it's really not a dipole that is like, wow, like, it's just so powerful. I mean, it is CO, but remember that the polarities in this case cancel out. This polarity goes to the right, this polarity goes to the left. So polarities to the right, to the left, they do cancel out, right? I mean, this component versus this component, right? This one will cancel out with this one. So you're only left with this dipole moment. So that's why it looks like it's going to be like, oh, it has a very strong polarity. No, because the polarities, they go in opposite direction, one to the right and one to the left. Of course, they will cancel out, at least in a very small proportion. Okay, so this one decreases greatly the boiling point of ethers. That's why they have a relatively low boiling point, which is not the case for alcohols. Alcohols are able to form very good hydrogen bonds because they have acceptors and they have donors in ethers now. And propane, of course, propane has no other choice. Propane has no hydrogen bonds and it has no dipole-dipole. So the only thing you can do is dispersion forces. Dispersion, that's all. In the case in the ether, thiol is a weak dipole-dipole, that's all. That would be the most, let's say, prevalent, right, intermolecular forces in ethers because it's not able to form hydrogen bonds. All right, so let's continue with the slides. Okay, so here is the dipole moments, right? The dipole moment for an ether. See, this dipole goes up to the right and this dipole goes up to the left, right? So if they go to opposite direction, of course, they will cancel out. They will cancel out because one is going to the right, the one is going to the left. There's another dipole from the lone pairs of electrons, but then that's it. The dipole created by the CO bonds, they cancel out. So the only dipole moment that you guys have is the one that is pointing up, mainly coming from the lone pairs of electrons. Okay? So here there are some common ethers that we have in nature that we use it at some point. Diethyl ether is one of them. We used it for some extraction in organic chemistry 1 lab. We use it in organic, for separatory funnels to do like an acid-base extraction or, like polar, non-polar solvents. Ether has a really low density, so ether is always going to float on the top of water, right? Or the aqueous layer. THF is the next one. Remember, I don't know, you guys recall that at some point, some reactions, for example, hydroboration. For hydroboration, we were using BH3 in THF. What is a THF? THF is a solvent, which is tetrahydrofurane. Okay? Dioxane is another solvent. This is right here. That's instruction for dioxane is a diether in a 6-member ring. All these three are very known organic solvents. Very toxic, yeah, unfortunately. Except diethyl ether. Well, depending on the dose, right? We always say like toxicity really depends on the dose of the compound. Okay, this one is very interesting part is the existence of something called crown ethers. Ethers, besides being a functional group, and they're also used as solvents, they're also used to mask some ions that are really not convenient for us, right? So I'll just give you one example, which is it's going to be very obvious for you guys. And then since you guys have re-study substitution reaction, right? So what happens if I want to do a substitution reaction of cyclohexyl bromide in sodium sulfide? Okay. The purpose of that is to produce, cyclohexyl sulfide. And of course, I have sodium bromide as a side product. So this one on the paper works perfect. But if you want to do it in the lab, what is going to happen? Okay, so let's do an analysis. What is the nature of that compound? This compound is non-polar. So is it going to be water soluble? It's not going to be soluble in water. Oh, Professor, but you have a CBR that has a dipole moment, right? Has a dipole here. Yes, but the molecule is predominantly carbon, hydrogen, CCCHs. You only have one CBR bond. So they will have some polarity, but really not enough to make it soluble in water because you have multicyclohexol. So the cyclohexol is very, very dominant. So it will be mostly non-polar. What about sodium sulfide? Sodium sulfide is an ionic compound. So as an ionic compound, of course, it's going to be soluble in water. So I have to dissolve this in water. So then if I shake these two, is the reaction going to work out? No, no, of course no. They won't mix. The sodium sulfide will be in water. And sodium sulfide hates this compound. Why? Because this compound is non-polar. Non-polar and polar or ionic, they're never going to mix. Then how can you make this compound? How can you produce this? If I want these two reactants to interact, I want them to collide. I want them to, to touch, to do like the nucleophile electrophile type of interaction. How do I do that if they are in opposite phases? Non-polar layer and polar layer, right? The polar aqueous layer and let's say like the organic layer, right? How can I make them interact? That's why in nature, they created what we call crown ethers. So crown ethers are really like mediators. What crown ethers are going to do, they're going to solubilize one of them. In this case, ether is organic. So, but it's an organic species, right? But it's going to work on your side, on your favor to treat ionic compounds to make them soluble. So what happened with crown ether? Okay, crown ethers come in different ways. Crown ethers are like, as the name says, they are ethers. This is a crown ether, for example, right? So the ethers are right here. Okay, you see how they form like a circle? Right? They form a circle and they have the oxygens in the middle. The oxygens in the middle, they are facing or pointing towards a cavity right here. There is a space in the middle of that macro cycle, right? It's a macro ring and it has a pocket. So inside of that pocket, you can have a metal. That metal will be trapped inside of that kind of ring, right? Like a kind of it's like a circle. So, and how is it trapped? Because all the oxygens are pointing in, right? Are pointing towards the middle. So this electron will donate electron density, electron density, electron density, electron, and it basically they're going to halt, right? It's like imagine like a ring, right? The ring has, I mean, the crown ether will be, I mean, basically trapped. So if there is a metal that goes inside, of course, it's gonna get captured. Okay. And of course, it depends on the sizes, right? So for example, this ring could be perfect for that particular piece of plastic. But if I want to put this piece of plastic, of course, I can't use the ring. It's too small. So what should I do in this case of plastic? Then if you want to do that, then maybe you want to use a bigger ring, right? So that's why depending on the type of metal, you guys can do, you guys can trap different types of metals. And then what is going to happen with this particular reaction then? So this particular crown ether, in the case of sodium, I think is crown. Let me verify so I give you the correct information for the sodium. If you want to trap sodium, you need a crown 5. So it's a crown 5. So you need 5. 1, 2, 3, 4, 5. That's crown 5. So I will mix sodium sulfide. And then what sodium sulfide will do with the crown ether will immediately trap the sodium. The sodium will be trapped inside the electrons of the oxygens. Of course, they will serve as holders for that sodium, depending on the size. Remember, guys. So the sodium is out. What happened with this with the sulfide ion? It will be free. Oh, is it going to be free? No, I mean, of course, it's going to stay close to the sodium, but it's going to stay close to the sodium. It's not going to be ionically bonded to the sodium. It will be, let's say, the sodium is bonded to the crown ether, and the sulfide will stay like that, right, next to it. But the sodium and the sulfide is not going to be attached to each other, right? So it's not going to be an ionic bond. So now the SH is available. So what happened with the SH in the next step? Well, you have the bromide. Now the SH is free in a friendly environment, right? Why? Because the sodium was trapped. So the ionic character of the compound decreases. Why? Because the sodium now is not ionically bonded to the SH anymore. It's only partially attracting the SH, but the sodium is attracted more to the crown ether. Yeah, of course, the sodium has 5 oxygens donating electrons. Of course, the sodium will prefer the 5 oxygens instead of the sulfur, which is only 1 ion. Okay, so the sulfide then say, like, okay, sodium, stay with the ether. In the meantime, I will do the reaction with the bromide. So we'll do an SN2 reaction, and that's how SH gets in, and then you have the bromide. Okay, after that, of course, you boil the ether will boil without the sodium, and then the sodium will just reform the bond with the Br. Okay, so, but that's the idea of the crown ether. Is like, the idea of the crown ether is really you have the ionic compound, you need to trap the cation. It's only for cation, guys, okay? So don't even think of doing it for anions. Why? Because the inside of the ether is negatively charged, right? Has a lot of electrons. Of course, if you have electrons, excess electrons, the only species that can go in are cations, because they're opposite, right? Opposite environment. So positive inside, and the electrons are, I mean, the oxygens are electron rich, so they need to be a cation inside. Okay, so that's really the job of the crown ethers. Very, very convenient way how to trap ions. Here you guys have 12 crown 4, 15 crown 5, 18 crown 6. Do we need to memorize those numbers? I mean, no, you don't need to memorize. I mean, if you remember them, that would be great. But you see, lithium is very small. So lithium needs a crown 4. What does that mean, the 12 crown 4? Well, the crown 4 means that you have 4 oxygens. The 12 means that that's the size, the full size of the crown. So it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 atoms in total, including the oxygens. But out of those 12, 4 are oxygen. That's why they call it 12 crown 4. And in solvates, lithium plus ions. In the case of sodium, you guys have 15 crown 5. You need a bigger crown. So that's why it's 5 oxygens inside of a 15, right? Part of a 15 atom, right? Crown. For potassium, of course, it's way bigger. So you need an 18 crown 6 solvates potassium. Okay, so this is a reaction, right? So this compound is definitely very hydrophobic. It's never going to be dissolved in water. So since it doesn't dissolve in water, I need the help of a crown ether. So the crown ether will help me to distract the potassium. The potassium gets trapped, right? You trap the potassium, okay? And then the fluoride is going to be free. Once the fluoride is free, it will do the substitution, okay? In this particular reaction. That's the shape more or less of the crown ether right here. You see how it is electron rich. The red areas are electron rich parts. So that's where the sodium will fit. Do we have crown ethers also for calcium, for ammonia, for other ions that are not other than the 1A of the periodic table? Yes, we can. We do. So I have even seen papers that they use the same crown ether for potassium, for calcium. So for calcium and potassium with the same crown ether. Why? Because they have about the same size. It really goes about the size. It doesn't go about the charge. You would say like, oh, are these trapped because they have a +1 charge? No, not necessarily. I have seen crown ethers that they can also, trap aluminum that has +3. They can trap calcium that are +2. It really depends on the size of the packet. Okay. And then to complete that idea, I mean, there is another paper that I found from the JACS, the Journal of the American Chemical Society. Here is in this image, you guys can see a really, really long, oops, list, right, of different types of I was looking at my channel for the videos. A lot of crown ethers. They're labeled by A, B, C, D. I mean, don't think that those letters are something. So this one is the crown 4. This one is also crown 4. But you see, guys, here they also replace nitrogen and oxygen. So they have oxygen and nitrogen. Oh, is this still called a crown ether? Yes, this is a crown ether because it has an ether. The oxygens are here, but you also have amines. So the amines, of course, they also have electrons, and the electrons can also be used as the same idea, right? So to trap an ion inside. Advantages, disadvantages, many advantages and disadvantages. The main disadvantage of the amino group is that the amino groups, remember, they are pH sensitive, meaning that the amino can be protonated, can be deprotonated, and that might cause some issues. Why? Because sometimes you want a particular pH for the reaction. So let's say, like, oh, I want to use KF. Let's say it's an acidic salt. So maybe it's going to be acidic. If it's acidic, maybe it will protonate the nitrogens. So that's bad. I don't want to protonate it. What else? Nitrogen is also nucleophilic. These nitrogens right here, they have lone pairs of electrons, and we know that nitrogen are excellent nucleophiles. So your crown ether might actually interfere with your reaction, giving you a side product which you don't want. And you have a lot. Remember, you're not just using 1 drop of 2 drops of crown ether. You add more crown ether. It's a lot of crown ether that you're adding. Why? Because you want to ensure that the potassium, the calcium, the magnesium, or the sodium, they are trapped. So you use a relatively decent amount of the crown ether. Okay, so the probability that the crown ether will react, yes, it will be high. Oxygens in an ether, they are not like that polar. So that's why they are not that nucleophilic. So the side reactions are really minimized. So here you have another crown ether. This one will be a crown 5, right? Type of crown 5. 2 crown 5s, look, 1 and 2. That also exists. Look, the type of crown ether you can do. There are some crown ethers with sulfur. The bad thing of sulfur is that sulfur polymerizes a lot and gets oxidized pretty easily. So it's a really very painful to use sulfur in organic chemistry. This one is a perfect one, 6, crown 6. But you see this crown 6 has like a staple here, right? So that's why they do some attachments. Sometimes they might even put a benzene ring. Here they have a benzene ring, maybe to make it more non-polar. The ring, I want the crown ether to be more non-polar. I don't want it to be that polar. That's why they add a benzene ring. Here's another benzene ring. They have here all the elements: oxygen, sulfur, and nitrogen. Wow, it's a lot. Here, a very big one. Maybe this one is a crown 8. 1, 2, 3, 4, 5, 6, 7, 8. Maybe for this crown ether, they want to trap a very, very large ion, maybe cesium or rubidium, which are very, very long, or barium. Barium is also a very big ion, +2. So depending on the type of ion that you want to trap, or maybe it's good for zinc, it's maybe good for palladium, it's very good for lead or mercury, any heavy metal, really, any ion, cation can be trapped inside of this species. Okay, so this is just to give you an idea, right? So what are the types, other alternatives, other types of ethers, and then also how they can be used. Okay, discussion about crown ether. Yes, please read or type of revise maybe what you find in Wikipedia, or maybe the textbook, whatever application that can be using of crown ether. Here they are using it for what? For stabilization of magnesium, for the Grignard reagent. Grignard reagent, if you recall, Grignard reagents are always made in ether. Diethyl ether is a solvent. Why is diethyl ether the solvent for Grignard? Because diethyl ether is able to stabilize the magnesium. It acts as a crown ether, but it's not really a crown ether because it is just 2 simple ethers, but the magnesium is stabilized by the presence of the lone pairs of the oxygens of the ether. right? Okay, now let's start with preparation of the ethers, right? So here now we're gonna prepare ether, and then the most conventional way of preparation, as we already know, for every functional group, we will be discussing the physical properties, which we already did, and now how to the preparation of the ethers and epoxides, and then reaction of ethers and epoxides. Okay, so this one is the industrial way how to prepare ethers. That's what they do to make those diethyl ether, methyl ether, diisopropyl ethers. This one only applied to symmetrical ethers. So for example, you can see I'm making two ethers here. So sorry, the same branches, right? The two branches are identical, and they are made by the acid treatment. So we need a very strong acid. I mean, it's a very strong acid like sulfuric acid, highly concentrated sulfuric acid from alcohol. So the alcohol will be used in the preparation for this ether. Okay, limitations, you can only use one unique primary alcohol, has to be primary alcohol, okay, to promote substitution. If you have like a more branch alcohol, secondary or tertiary, what you will guys will do is mostly elimination. Remember when we had elimination with sulfuric acid to produce an alkene? Well, that happens because you have a secondary or tertiary. Primary mostly undergo substitution. So that's why is more convenient to do with primary alcohol. So for example, diethyl ether, perfect. You just use ethanol, two carbons, sulfuric acid. The mechanism is right here. I don't need to rewrite it. It's a very simple mechanism. So the OH, do we need to know this mechanism? Yes, we need to know this mechanism. So the OH attacks the H, right? It's protonated. You get an ethanol protonated. Then the second ethanol, which is neutral, will attack in an SN2 style from the backside, right? It's a backside attack, attacks the carbon from behind, and the water leaves. Okay, now you have an OH protonated, the ethanol, a second ethanol will take that off. Okay, and then you get the diethyl ether. Using mixed alcohols produces several ethers. Yeah, if you use two different alcohols, let's say I have 50-50, a mixture of ethanol and methanol, well, you will get three types of ethers, right? So that's one of the disadvantages of this, maybe of this technique, is that you can only use it with symmetrical, to make symmetrical alcohols. So let's say I have these two alcohols and I decide to use sulfuric acid concentrated. So of course you're gonna form three ethers. Who are they? The self reaction with the ethanol, the cross reaction will be this, and the self reaction of methanol with methanol. Okay, so three ethers will be created in this particular reaction. So that's why it's not the most convenient way how to make ether. So you either do it with ethanol only or with methanol only, but never use a multiple. If you add a third alcohol, it will even be more complex, right? So let's say if you put cyclohexanol. If you put cyclohexanol, you will get also this ether, right? The self, then the cross of these two, right? Then the cross of these two. Right? You will get 6 ethers in this case. Yeah. 1, 2, 3, yes, 3 each. If it's 2, I get 3. Yeah. Okay, so those are the only possibilities for ethers that you can get if you're doing this technique. Of course, nobody wants that. Nobody wants to purify. I mean, they might have very, different boiling points, but still, I mean, nobody wants to go through that purification step. Right? Great. What do we do then to solve that problem? Now we are having another named reaction. The first named reaction that we learned was last chapter about the Grignard, right? Grignard reaction. Now we have the Williamson ether synthesis. It's just a named reaction, but really it's an SN2 reaction. Okay, so don't get scared by the reaction. It's nothing new. It's just like it's a variant, an application of an SN2 reaction. So in an SN2, in this particular reaction, we use an alcohol. We deprotonate the alcohol with sodium hydride or pure sodium, metal sodium. Biprotonates the alcohol becomes an alkoxide, and that alkoxide will attack in an SN2 style the alkyl halide. So you need an alkyl halide and you need an alcohol. The alcohol has to be pre-treated. The alcohol is pre-treated with sodium hydride or metal sodium to get deprotonated. Once it's deprotonated, it will attack in an SN2 style your it will attack the alkyl halide. Right? But the main idea is that you always remember that this is an SN2 reaction. SN2. So SN2, remember, what do we remember from SN2 reaction? Okay, well, in SN2 reaction, what I remember, Professor, is that the reactivity trend was methyl, followed by primary, followed by secondary. And tertiary had very small chances to react in an SN2 reaction. Okay, so I always prefer methyl, primary, secondary. Do I need to know the mechanism for the Williamson? Yes, you guys have to do it. Okay, so let's say that they tell me, do the Williamson reaction synthesis between isopropanol, sodium hydride, followed by butyl bromide. Okay, mechanism for that. The goal is to produce this ether. Okay, in the first step, you guys have OH, you have hydride. Okay, remember that the sodium is an spectator, the sodium does not participate. So the hydride will attack, okay, attack the electrons, will attack the H, this bond retracts, right, to the alkoxide. I form the alkoxide. What happened with the hydrogen? The hydrogen got H2. It's a gas, so it doesn't really matter. So all I'm using is the alkoxide. Now the alkoxide will attack in an SN2 style the ethyl bromide. So the ethyl bromide, see, the electrons attack the bromide, right? The carbon with the bromide and the bromide leaves. Anything new? No. Same thing as Orgo-1 substitution? Yes, the same thing. But it's a sequence of events. I would use the hydride. Don't use the metal sodium because the mechanism we haven't learned it. So just use sodium hydride. Okay? Sodium hydride, the hydride deprotonates, you form the alkoxide. And the alkoxide attacks the halide. Okay, now going back to the idea of the primary, secondary. Okay, and then that's really for synthesis purposes. So whenever you guys see an ether, you guys have to think and that's part of the synthesis, portion of this chapter is like, whenever I see an ether, I should be able to break it down. Okay, you show me this ether. This ether was synthesized from the Williamson ether synthesis. So if this one is coming from the Williamson ether synthesis, then this one is going to be either the alcohol or it can be the halide. Or this one is going to be the alcohol. Oh, sorry, of this one, right? If this one is the alcohol, then this one is going to be the halide. If this one is the halide, that means that this one is going to be the alcohol. So how do I decide? How do I know which one is which? Remember that it's an SN2 reaction. If it's an SN2 reaction, it prefers methyls, then primary, secondary, and tertiary is my last option. So my alkyl halide has to be methyl. If there is no methyl, primary or secondary. So which alkyl halide is the most convenient? If I choose this one would be a primary alkyl halide because the ether is attached to a primary carbon. If I go this side, this one will be a secondary alkyl halide. Why? Because the ether carbon is attached to two other carbons, meaning that it's secondary. So which one is more convenient for my Williamson ether synthesis? This side to be my alkyl halide and this side to be my alcohol. Why again? Because this alkyl halide is primary and the Williamson ether synthesis follows the SN2 trend. The SN2 trend says tertiary, primary, secondary. So if that's the case, that means that this guy has to be the alkyl halide 1,2 bromide, and this other side has to be the has to be the alcohol. Of course, this alcohol is going to be treated with the sodium hydride to form the alkoxide, right? But that comes next. I mean, that's something that you guys don't have to show, but that's really, right? Then this react with this, right? And then that's how you produce, right? You produce that final compound. But that's the idea. That's the rationale. That's the way how to understand a Williamson ether synthesis. So what if both of them are the same, Professor? What if you give me this option? Let's say this ether. What should I do in this case? Yeah, in this case, it doesn't really matter. Why? Because this carbon is secondary and this carbon is also secondary. So there is really no point. I cannot decide. Oh, because it's a ring, maybe it's better because it was an open chain, has more freedom. No. In the case of secondary, they are both secondary. So both secondary, the reaction will be almost the same. So very, very tiny differences, but of course, it's the same. So it doesn't matter. You can do this one as alcohol or this one as RX or this one as RX or this one. Doesn't really matter. Okay. Let's give some more example for the Williamson. Let's say if you guys have this compound. Okay. So what was my study material? Which one was my RX and which one was my alcohol? You might be saying, oh, professor, we're the same situation. This carbon is secondary and this carbon is also secondary. So it doesn't really matter which one is my alcohol, which one is my halide. Not true. Because remember that tertiary, right? Sorry, SN2 reaction says that the reactivity trend is methyl, primary, secondary, tertiary. But aromatic compounds do not react. And double bonds, right, attached to a halogen, they don't react either. So they are not reactive in an SN2 reaction. So that means that this guy can never be a DRX because the SN2 reaction does not, right, work with aromatic compounds. So what is the only option for this particular side? It has to be ROH, has to be the alcohol. If this one is the alcohol, this one has to be the RX. Okay, so that means that if this one is the RX, it would be this one, cyclohexol bromide. I'm not using bromide just as an example. I mean, it can be chloride, can be iodide. And this other rest could be the has to be the alcohol. Well, in this case, it's not an alcohol, it's a phenol, but that's my only option. We can do this other set. Please don't do this, right? Because the other combo would be these two. But the problem with these two is that this one has an aromatic. It's an aromatic halide. And aromatic halides, they don't do SN2 reaction. Okay, so I can't use this set. This set has to be blocked. So the only option is to use this combo. Okay, this combo is the one that is the only one that is going to allow me to produce this compound, this ether. All right. Okay, so let's do more examples. I mean, I know you guys like examples. Let me get some more. Okay, so let me see if I have a chirp. You don't know. Okay. Yep. So tertiary, right? Tertiary, primary. Tertiary, primary. So which one is going to be my RX? This one has to be the RX. And this one, of course, the tertiary side has to be the alcohol side. Okay, break it. The RX will be this side, no oxygen, right? So it has two carbons, ethyl iodide. And this other side is going to be my alcohol. So it will be terbutanol. Okay. So I have to combine these two, the halide and the alcohol. And that's it. That's the Williamson ether synthesis. It's always a center reaction, alcohol. The alcohol has to be treated with hydride to deprotonate it. It has to be deprotonated. Do not leave it without deprotonation, please. Okay, so it's not just by simply mixing those two. No, you have to pre-treat your alcohol, get the alkoxide. Once the alkoxide is prepared, then it can be exposed to the alkyl halide to produce the ether. right? Before that, don't just plainly, right? Simply mix those two. No, 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 it won't work like that. So you need to make it a better nucleophile because as an alcohol, it's a weak nucleophile. Remember, the SN2 reaction, they need a strong nucleophiles. So that's why to make it a strong nucleophile, just deprotonate it with sodium hydride. Sodium hydride will give you the alkoxide. Once it is an alkoxide, it will be an SN2 nucleophile, a strong nucleophile that can attack your halide and then produce the ether, right? Good. Another case, right? Because I know that you guys have questions. Professor, what if I want to make two tertiaries? Can I make this guy? Yeah, that's challenging, right? Because remember that this one is an SN2 reaction. If I have tertiary, what should I do? Yeah, in that case, it's very difficult. So my recommendation in this case is only just use the previous case, the previous reaction, in which you guys have to use sulfuric acid concentrated. That's my only option, what I would say, that's the only way how you can make this type of highly substituted ethers. Okay, that is if it's symmetrical. If it's non-symmetrical, then what should I do? Right? Yeah. Hopefully you never find those those challenging questions. But with the tools, the reaction that we know so far, yeah, we cannot make those like tertiary, non-symmetrical, right? Ethers. So I would say just just use that in the worst case scenario, the concentrated sulfuric acid. The Williamson is not going to work. This one cannot work because it's tertiary. Tertiary, of course, is never going to give you Williamson ether synthesis. Okay. Great. So here are the same rationale I was telling you. If there's a phenol, the phenol has to be the alcohol. That's why they put the OH here. That's a primary. Primary will give you the ethyl, right? Ethyl halide. So alcohol with sodium hydroxide. Oh yeah, in this case, sodium hydroxide. Why do they use sodium hydroxide in this case? Because it's a phenol. Remember in the previous chapter, we were saying that phenols were way more acidic than alcohols. This is not an alcohol, it's a phenol, but it can still be used for the Williamson ether synthesis reaction. Okay, so it will deprotonate the OH, right? Giving you the phenoxide. The phenoxide will react in an SN2 reaction with the ethyl iodide, giving you the ether that you desire. So here is telling you, right? So these are the two options to produce an ether. So terbutanol, sodium hydride, methyl iodide. Good, because the methyl iodide is a methyl halide. It's good for SN2. This one is a tertiary iodide. Tertiary iodides are really bad for SN2 reactions. So that's why this reaction is crossed out. It will not work. So the best option would be to go this way. All right. Good. Another way how to make ethers, a little bit underestimated from in Orgo 1 is the alkoxymercuration. We normally call it oxymercuration, but this one can be changed a little bit and then be called alkoxymercuration. If you recall from the reaction is mercury acetate in water, followed by the use of sodium borohydride. In this case, the water is the one that breaks up. The water breaks into OH and H and gets added to the alkene with no rearrangement and in a Markovnikov style, right? We can change that. Why? Because the water can be replaced by an alcohol. The alcohol can be methanol. So the methanol will break also into CH3O and H. And now you get an ether inside, okay? Examples for that. Okay, let me give you the example. Cyclohexene, right? I use it with mercury acetate in methanol, followed by sodium borohydride. Okay, in this case, the alkene breaks. Well, no, doesn't break, but the alkene, yeah, the alkene disappears. And then one of the carbons, the Markovnikov, will get the CH3O. In this case, there is no Markovnikov, but COCH3. And the other side will get the H. And that's what I will get. Okay, makes sense, right? The CH3O. If it's ethanol, of course, it will be ethyl here. If it's propanol, propyl here. Cyclohexanol, cyclohexyl here. right? So that's how you guys will get. In this case, there is no Markovnikov. Let's give one example with the Markovnikov case. The case of the Markovnikov, let's say that I have right? I'm doing the reaction with mercury acetate. This time let's do what should we do? Ethanol and sodium borohydride, right? So the methanol, the the ethanol, right? The ethoxy, that side will go to the Markovnikov. This one is my Markovnikov side. And the H will go to the anti-Markovnikov. Okay, good. So it will go there. It's ethanol, right? O, CH2, CH3. And the H, of course, will go to this side, but the H is not written. This molecule is chiral, so you guys will get that, and also the enantiomer, right? Because it's chiral, only because of that. You get two products here. But you see is the ethoxy side. The ethoxy side goes to the Markovnikov. No CCR, no rearrangement. CCR means carbocation arrangement. So there is no migration here that occur, right? Great, so let's continue. Okay, another one. Now is reactions of ethers. What type of reactions can be involved with ethers? So the same way how you can form ethers, you can also cleave ethers. So the cleavage of the ethers is mostly done in acidic conditions. So we will have the acidic cleavage of ethers. When you have it in front of you, you will use a strong acid on excess with heat. So basically we do it with reflux. So excess HX. The HX can be HCl, HBr, I think the HI can still be done. Right? So excess, no HF because HF is not, fluoride is not a good nucleophile, so that's not a good idea. And you guys will cleave the ether and produce two alkyl halides. Do I need to know the mechanism for this? Yes, you also need to know the mechanism for this reaction. Okay, so the reaction is maybe here is a little bit more complicated. Let me do it by myself. I'll do it here. Let's use isopropyl, ethyl isopropyl. Okay, I use HCl. Okay, since it is concentrated and excess, this one will attack the H. The Cl leaves. Okay, you see here the H plus. Okay, it gets protonated. The Cl minus. Cl minus is a strong nucleophile. So the Cl minus will break it from the least substituted side. And that's very important to remember because you might say like, oh, professor, it doesn't matter because I'm going to also break the other ether. So it doesn't matter which one I attack first because both of them are going to get broken, right? It's like I'm going to break my two fingers. Does it matter if I break this one first or this one later? If they are both going to get broken? In terms of mechanism, yes. So if it is a mechanism, you have to break first the weakest one, right? The easiest to break, which would be the index, right? So, and then you will break the middle finger, right? So that's really the how the mechanism should be written. Always the logical and sequential, right? Process or steps that the reaction will undergo. So chloride is a strong nucleophile, a strongish, medium strong nucleophile, but still will do an SN2 reaction. So the chloride will attack the least attituted. That's my least attituted. And this bond will retract. Okay, so I will form first the ethyl chloride. That's the ethyl, 1 and 2. 1 and 2, and this one goes to the oxygen. So you will get isopropanol. That's the second one. Huh? Now it's neutral. Now in excess HCl, the alcohol will again deprotonate the HCl, right? The HCl will be involved. OH2 plus. That OH2 plus will be exposed again to chloride. That chloride now has no other choice than attack that carbon. Now has no option, right? In this case, you have the option because you can attack the primary or the secondary. Of course, it will prefer to attack the primary because it's less hinder. Here the chloride has to attack the secondary, so it will attack and then give you Cl, which is your second product. That was your first product. And of course, you lose water. Okay, water is lost. That's it. Two chlorides, yeah, you need two chlorides, and then yeah. The two chlorines are here, the H's are in the water, right? And the oxygen came from the ether. Okay, so that's the mechanism, example of mechanism for the cleavage. I use HCl, but once again, you can use anything you want. Here, why this one didn't give you halogen here? Because you have a phenol. Remember, phenols can never be substituted. Okay, so because it's a benzene ring, so benzene rings cannot undergo substitution. Okay, but you can still do the R side. It's only that the cleavage will not do it. Okay, so that was all for ethers. Now is the turn of cyclic ethers or epoxides, what we call epoxides. Epoxides are cyclic ethers. It's just really the cyclic version of an ether, but they have to be under strain, under angular strain. So that's something new. Well, it's not new for some of you, but if you guys didn't take the class with me before, angular strain. Okay. What is angular strain? Angular strain is when a hybridization loses its angle, right? So for example, sp3, right? The sp3 has a 109.5, I think. So yeah, 109.5 degree angle. The sp2 hybridization has a 120 degrees, and the sp hybridization has 180. So what happens if you have a an sp3 carbon, right? Which is supposed to have 109, and then you squeeze it in a way that is in a four-member ring. Four-member rings, they have 90 degrees, right? So 90 degrees are not that friendly for an sp3 hybridization because sp3 hybridization is 109 degrees. 109 to 90 is like a 20 degrees squeeze, right? You're squeezing it by 20 degrees. It's kind of rough for that. And if you squeeze it to even a three-member ring, that's a 60-degree angle. So you're forcing a 109 to a 60 degrees. That's a big one. So that angular, we call it angular strain, is that force against normal conditions that takes an angle that is supposed to exist at a particular value, you squeeze it to a way smaller angle. It will give you what we call angular strain. And that angular strain will make epoxides highly reactive. Okay, oxirane, right? It's a ring system, a three-member. An oxirane is an epoxide. Oxetane, right? So it's a four-member ring, oxolane and oxane. For example, dioxane, right? Dioxane was one of them, but dioxane is not an epoxide. It's not like that strained, right? So five-member ring is still good. Oxetane, yeah, maybe that one has some strain, but the one that has most of the strain, the angular strain, is the oxirane, right? Why? Because the angle is forced from an sp3 hybridization angle to a 60 degree angle. So there is a lot of tension there in that particular carbon that makes it very reactive. That angular strain, we make those two carbons very receptive. So if they can find a way to open up, right, to release that strain, they will do it. Where do we find epoxides? Epoxides, as we said, they are very, very unstable. They're very reactive. So we find them in compounds that they don't last for too long. For example, the sex pheromone, right, of a moth, right? So, of course, the moth only wants this pheromone to be around for a few seconds. I don't think that the moth wants to be, right, secreting pheromones for a month or for a week. Why? Because, you know, it's the sex attractant, right? So it will attract the male for too long, so it's not good for the moth. So it will just do it for a very short time. So since this epoxide is very reactive, it will only last seconds, maybe a couple of minutes, right? And after that, the epoxide, of course, is going to react. So it's not going to be active anymore. Same thing here, another sex pheromone for a cockroach, right? The cockroach, that one is, that's really gross, but it's also a sex attractant between animals, and they shouldn't last for too long. So that's why they have epoxides. The epoxide will be a very short life, right? Short life compound or molecule that will last only a few seconds or minutes, or depending on the conditions, right? On the weather conditions for those molecules to survive for a longer time. For example, moisture, heat, right? Those are factors that will affect the longevity, right, of this particular species. Okay. Preparation of oxidations. Okay, how do we prepare or how do we make epoxides? We learned those two already, the ways how to make epoxides. We are not going to be learning more. Those are two ways: MCPBA, metachloroperoxybenzoic acid, that's one of them. NCPBA, or I mean, it can be called also peroxyacetic acid, any peracid. Peracid is any of the acid that is used for the preparation of all epoxides, but the most conventional is the metachloroperoxybenzoic acid. Okay. So it's a very long name. Of course, it has to be abbreviated, and that's really I'm going to tell you, the kind of like a really fun thing that happened to me. You can skip it. I mean, you don't want to hear it, you can skip and then cut this recording. I'm going to be talking about that about 2 minutes. It starts now. Once I went to a nutritionist. Okay, and of course, the nutritionist, she didn't know I was a chemist. I just walking. I mean, you see me on the street, normally you won't notice I'm a chemist, but I just went there. I don't know what. Maybe she thought I was. Maybe I was like I don't know. Whatever is, the idea that I give when somebody sees me for the first time. So, no idea, no clue. And then I was telling the nutritionist, I said like, oh, I'm taking this multivitamins. I mean, is that good? I also have some knee pain from the sports that I play, I practice. So I would like, are these things good for that? What do you think about this? I mean, I see that has some sugars, has some, some amino acids. I just want you to, to give an opinion, right, from the nutritionist. And then she didn't have a clue of what, my profession. And then she said like, why? She tells me like, why are you taking this many, drugs or, like pills? So it's too many. I bet you $5 each that you cannot even pronounce the names of these compounds. Okay, I said, okay, let's see, let's try it. And then she pointed to one by one of these compounds. And since those words are so familiar to me, I could just fluently say, like this metachloroperoxybenzoic acid, or, like paraminobenzoic acid, and then, or say like glutathione, or, like this acid. And then she was just pointing word by word, and this one, and this one, and this one is the phenolaniline, like phenolaniline hydrochlorate, or, things like they were written. And then I was just like reading one myself, like, how can you read it? I cannot even read it. Oh, no, they're easy. They say like, no, how can you use, they are not common words in English. I say like, I know. But I'm a chemist. That's why I know. That's why you're cheating. I'm not gonna pay you anything because of the. And that's an experience that some compounds, they have a very long name. Like that's the take home story. The take home message is that the words are very long, and in chemistry you will find very long names. That's why we use abbreviation. THF was one of them, right? Tetrahydrofurane. NCPBA is metachloroperoxybenzoic acid, right? So there's another one, the PBA, paraminobenzoic acid. PBA is another one, right? So LSD is another one, right? So there are many abbreviations that we use for compounds. LAH, lithium aluminum hydride, right? So there are many compounds that it was very funny. I mean, it was very funny that moment with the nutritionist that she had no idea how come this short Hispanic guy knows how to pronounce these complicated words. Anyway, all right. So let's go now to the preparation of epoxides, right? So preparation of epoxide can be done with NCPBA, metachloropyroxybenzoic acid. Yep. So it's made from alkenes. Yep. So here is one of them. It preserves the stereochemistry. Be very careful with that stereochemistry. So if your alkene is cis, your epoxide will also be cis. If it's trans, the epoxide will also be trans. Okay, so here, see the differences between cis and trans, cis, trans, trans. Okay, so that's very simple. We don't need to know the mechanism, no mechanism for the NCPBA reaction. Another one that maybe is not like that common that we have studied in organic one is the halohydrin formation. Okay, so the halohydrin is a reaction that we study on chapter 8. Okay, you guys have an alkene, you use bromine in water. Bromine in water give you a halohydrin. We don't need to know the mechanism, so only just is halohydrin. That's what I'm saying, telling you, right? Halohydrin. Halohydrin will give you the bromine and the OH trans. Okay, so if that bromine is, I'm just gonna put it here back. Okay, so that you see that OH and bromine trans, right? Yeah, of course, you will get two stereoisomers of the same, right? Because it can be OH up and Br dash down, right? Or Br up and OH down. So those are stereoisomers, okay? And you deprotonate them. So you deprotonate it with, so in this case, sodium hydroxide. Professor, how can you produce sodium hydroxide? You said that OHs are not good for alcohols. True, but this alcohol is with induction. So it decreases it increases the acidity, decreases the pKa because of the bromine. The bromine, the adjacent, the neighboring bromine makes this alcohol more acidic. If it could be this, yes, it wouldn't work. But because of the bromine, it does work because it increases acidity. So the sodium hydroxide will deprotonate the alcohol, giving you an alkoxide. And then here is where the magic will occur. Okay? So the bromine is trans. So the bromine is trans to the alkoxide. So the alkoxide will do an SN2 reaction because it's from the backside, right? It's the backside attack. So you guys will produce the oxide. Okay. This mechanism you don't need to know, but it's good, I mean, for you to understand what happens. How do you create the epoxide? The other way to avoid all that is to have the cyclohexene and use NCPBA. NCPBA, and NCPBA will give you the epoxide. That is if it's symmetrical. If it's non-symmetrical, let's say you have this alkene, right? Yeah, if it's this alkene, if you have NCPBA, yeah, you guys will get two epoxides. But just feel free to use the one that is more convenient for you, right? That epoxide plus that epoxide. You will need two epoxides, epoxide wedge or the epoxide dash. Why? Because the molecule is not symmetrical. See, if I trace a plane of symmetry, it's not, the sides are not symmetrical. No. In this case, yes, because there is a plane of symmetry. So the wedge and the dash epoxides are the same. In this case, they are not. Okay, so that is with NCPBA. Make sure that you remember about the cis and trans, right, case that we were seeing on this slide, cis and trans. The NCPBA does respect the stereochemistry, right, of the alkene. Okay, so you are producing the two, right? The two epoxides. Yeah, in the bromine, it will be the same case. If you are doing it with the halohydrin unfortunately will also give you the mixture of the two epoxides. So what you will say, like, Professor, I don't want the mixture of epoxides. Why do I have to be stuck with the mixture of epoxides? It's going to be very difficult to separate epoxides later on. Yes, if you wanted a very conservative synthesis, let's say in the industry, Johnson & Johnson, BASF, or Roche, or you know, like Gilead, or if you are working in, let's say, in Pfizer, right? So they are very conservative. It's not the same thing having this enantiomer or this enantiomer. They want to be very specific, right? So what should I do then? So there was somebody that worked on that. That's called the Sharpless. Sharpless is the scientist that worked on this particular issue, and he noticed that epoxidation, or the epoxide formation, can be selective, and he called it enantioselective epoxidation. Enantioselective epoxidation means that you can selectively produce one of the enantiomers of the two epoxides that can be made from this reaction. This reaction will give you two epoxides. This epoxide, they are enantiomers. What if I want to favor only this, 100% this and 0% of this? Or if I want 100% of this and 0% of this. Can I do that? Yes. And that's what Sharpless, right, was working on. He worked with catalysts, chiral catalysts. He says his hypothesis was like, if you have chiral products, and if you want to favor one of them, the only way how you can favor a chiral product to be more, you know, enhanced or rich in your product is by using a chiral catalyst. So you were using something similar to NCPBA, right? This one is the peroxyacetic acid. Is similar to the NCPBA. He used a catalyst precursor, and he used a chiral catalyst, DET. DET is I mean, this one is a tartaric. I remember it. I took it in grad school. I remember it was tartaric acid. The same as tartar sauce. Have you guys heard about tartar sauce? Yeah, same thing. So it's called tartaric. I'll write it. Tartaric acid. Okay, tartaric acid is that DET. DET is that T comes from tartaric acid. The DE means from the diethyl. Do we need to know that? No, no. I'm just sharing what it is. So this DET is chiral. You can see, right? It's chiral. Here has wedges and dashes. These carbons are chiral. These carbons are chiral. So the diethyl is coming from here. Ethyl. That's why they call it DET. So one is one enantiomer and the other is another enantiomer. If you want this particular enantiomer of the epoxide, you use one of these chiral tartaric acids. And the other enantiomer will be used for the production of the other epoxide. Okay, so this one is the titanium tetraisopropoxide. That titanium tetraisopropoxide was, you know, it binds to it. I don't think it's the complex. Yeah, back in my days, we had to learn the complex, yeah, how that happens. But, you know, what I'm trying to say is that titanium and the tartaric acid, they form a complex, and you can see by the shape of the complex how only one epoxide can be formed. Why? Because the wedges, they block one side of the epoxide, right? Or the alkene. They only expose the other side. So that's why the epoxide happens on the open side. The other tartaric acid, the enantiomer, blocks the opposite side, right? So it's, for example, imagine that you are, right? For example, I have this tape, right? So this one is my alkene. One of my enantiomer, let's say it blocks this side. The enantiomer blocks that side because it's my R enantiomer, let's say. So the epoxide will form on this side. It will form here, this COO. The other enantiomer, since it's the enantiomer of the catalyst, it will now bind to the opposite side because it's the enantiomer. It binds the same way. It binds with the same strength, but it will only bind to the other one, or the other side. Why? Because it's the enantiomer, right? What is on this side for this compound, remember the other one is the mirror image. So if you see the letters here, that's one of the enantiomers. In the other enantiomer is going to be the mirror of this. The mirror of this is this. So it will bind the other side. So where is the epoxide going to happen? The epoxide will only happen on this side. So that's why one enantiomer produces one of the epoxides and the other enantiomer produces the other epoxide from the other side. So it's all about 3D arrangements, right? So, or how the complex forms. That was one of the questions for my exam in grad school. So that's why we remember clearly, right, how this happened. But yeah, that's the idea. That's the full idea of the Sharpless epoxidation. Because of that, this diagram only tells you that catalysts, the only thing that catalysts do is decrease the activation energy. Okay, because of that, Barry Sharpless, right, he received the Nobel Prize in 2001. It wasn't not too long ago. I mean, some of you were, we're seeing the sunlight for the first time, but it was not too long ago. I mean, if we consider the Grignard reaction, if we consider the Williamson ether synthesis, yeah, this reaction is way newer than than those other reactions. Okay, so professor, what do we have to study from this side, right? So what are you teaching us? Is the enantioselective epoxidation. So you guys have to explain me, right? So what is enantioselective epoxidation? Enantioselective epoxidation is a reaction in which one chiral catalyst favors a particular chiral product, right? So of course, that only happens if your product gives you potentially two products, right? If you have two chiral products, right? Two enantiomers as products, then you use a chiral catalyst. The chiral catalyst will selectively produce and prevent, right? It will enhance one reaction and inhibits the other reaction. And the other enantiomer will enhance this reaction and inhibit the other reaction. Right? So we'll always lower the activation energy, but really the main part or the importance of this reaction is that it will is the separation of the enantiomers, right? The enantiomer products. So here this I am also telling you the formation of one enantiomer, formation of the other enantiomer. So both enantiomers will be favored because of the catalyst, right? But one of them will only favor one of the enantiomers. For example, this reaction, a higher activation energy for one of the enantiomers, right? So this green enantiomer will not occur. Why? Because the red enantiomer has a lower activation energy, so that red enantiomer will be the best and the one that is going to be produced because it has a lower activation energy. Okay, good. Let's continue. Acid-catalyzed opening of epoxides. Okay, so epoxides can be opened in two ways. So now we passed already the synthesis of epoxides. Now let's go to the reactions of epoxides. Okay, in the case of a reaction of epoxides, we can open the epoxide in two different ways. And we need to know the mechanism for both. Okay, so the acid-catalyzed and actually, let me open it here so you guys can see it. Acid-catalyzed and also the base catalyzed or nucleophilic opening of epoxides. Okay? Those are synthesis reactions that you guys can do. Actually, I don't want to spoil it. That one actually I want to leave it for you. This slide has only, has few. Okay, but it has the acid-catalyzed opening and the nucleophilic opening of the epoxide. They are different, right? But let's see. Okay, we're close to the end. We're not that far from the last slide. All right, so epoxides. We have this epoxide, and the epoxide can be opened, right? Remember this angular strain. The angular strain will be, let's say we have acid, and we have H3O plus. Yeah, let's do it. What is going to happen with the H3O plus is, I shouldn't have written it like that, but that's a better way to write H3O plus. So the oxygen, as always, it will protonate. It will get protonated by the H3O plus. Don't forget these arrows. These arrows are very important. OH, right? OH plus and water, right? I lose the water, but the water is not important at this point. Not yet. Okay. I'm going to bring it back. The water comes back. Why? Because I'm going to be using that water as a nucleophile. Why is it a nucleophile, professor? It's a nucleophile because this O plus right? The oxygen hates to be positively charged. So the oxygen, what it's going to do is going to transfer by induction delta plus to the neighboring carbons. Okay, so if this transfer, why? Because the oxygen cannot be attacked directly by a cannot be attacked by the nucleophile, because oxygen has electrons, of course there's going to be some repulsion, so it has to attack a carbon. So the oxygen will attack this carbon. Professor, why this carbon, why not this carbon? In this case, because this epoxide is symmetrical, so it doesn't really matter which one you attack. Okay, attacks this one, this carbon breaks the octet, so it will retrieve, open, this oxygen now gains two lone pairs, and this one has the OH. Later on, I have to deprotonate that. Another water molecule will deprotonate. And that's your product. Okay. OH, 1, 2, OH, OH, 1, 2, OH. Okay, that will be the mechanism for this ring opening. Acid-catalyzed epoxide opening. Right? You open the epoxide for that acid-catalyzed. That's the mechanism. Okay, this is a symmetrical epoxide. What if I don't have a symmetrical epoxide? What if I have a non-symmetrical epoxide like this one? Can I open this epoxide? Yes, you can also open that epoxide. Let's use acid CH3OH2 plus. Those are different ways how to write the same thing. So what you guys have here is methanol in acid. That's one way to write it. You can write CH3OH2 plus. That means that the methanol is protonated, or you can just write methanol in H3O plus. That's another way. Okay, they're all the same. Methanol in acid, protonated methanol, methanol in H3O plus, exactly the same thing. They all mean the same thing. Okay, so let's do the mechanism for that. Okay, right. So that is the CH3OH2. Epoxide gets protonated. Plus, right? Now here, now it's non-symmetrical. What should I do if it's non-symmetrical? Okay, if it's non-symmetrical. So remember that in my first mechanism, right? I was putting delta pluses here. Delta pluses. So you will put delta plus here, delta plus here. But now that's something very interesting happens. Right? Very interesting. So what happens is that they are not the same substitution. So if you have to move the plus to one of the carbons, where would you move it? Who is able to handle the plus charge more efficiently? Remember the stability of carbocations? Stability of carbocations says that tertiary carbocations are more stable than secondary carbocations, and secondary carbocations are more stable than primary carbocations. The same thing will apply stability of delta plus carbons. Delta plus carbons, tertiary delta plus are more stable than delta secondary, than delta primary, the same stability. So if the epoxide, the protonated epoxide has to decide, where should I move my charge better? I should move my charge maybe more to the tertiary carbon, So it will be a delta plus versus a delta plus. It will be mostly delta plus on this side than on this side. Why? Because the one is a tertiary carbon. Tertiary carbon can handle the delta plus more efficiently than this primary carbon. Okay, so the same thing, tertiary versus secondary, or secondary versus primary, the higher order will definitely stabilize the charge better. So that is what the oxygen decides to distribute the delta pluses. So knowing that, the methanol will feel that this tertiary will be more activated. or will be more receptive to the nucleophilic attack. So the methanol will attack that carbon. What about this carbon? Very small proportions, mostly here, because this one is where the delta plus is mostly located. Okay, so methanol attacks there, epoxide opens. This oxygen opens, so that's why I folded it. This one, let me put a color so you guys can recognize what is what. Okay. That would be that carbon. This other carbon, the blue carbon will be this one. And of course, the methanol should come from the other side, right? Or CH3. And the two methyls are here. Kind of trans, right? You have to see the trans. It always opens trans. Okay, so after that, we'll have to deprotonate it with another methanol. Methanol. Don't forget that deprotonation, guys. Okay, because you obtain CH3O plus, OH plus. So it has to be deprotonated. 1, 2. Yeah, right. Product. And you can see that they are trans, right? Here, I don't really need to show you that is wedge or dash. No, because you can see by the geometry that it's trans, right? The CH3 is trans respect to the OH. For example, I would need wedges and dashes if I put the CH3OH up here, because that one I cannot clearly see that they are trans. Here I see that they are trans. Okay, as long as you make me, you write it in a way that it's clear that you're producing a trans product, that's enough. Okay, so that is really what happens with acid catalyzed. You always favor the most substituted carbon, because the most substituted carbon is the one that is able to handle better the delta plus. That's why it goes to this carbon and not to this carbon. Good. Okay, let's continue now with the nucleophilic opening of epoxides. Now it's the opposite. Now you don't have any acid. So now let's say that you guys have an epoxide, the conventional epoxide, and you open it with a nucleophile. What is a nucleophile? Let's say sodium cyanide. Yeah, sodium cyanide. Remember, in sodium cyanide, even though it's written like that, the sodium is a spectator. So really, the one that is doing the job is the cyanide. So in the case of the cyanide will also feel the angular strain. These two carbons are under angular strain, and the cyanide will open one, attack to one, and then it will withdraw. Okay. Cyanide, and in a second step, you add H3O plus. It needs to be a H3O plus for the protonation of the alcohol. Trans, right? You see how I show it trans? I don't need to put wedges and dashes as long as you guys show it like that. That is trans. Okay, so that's what we have on these slides. Let me just put it for you guys so you guys remember. Oh, here. Okay. Oh, they put water. You can put water or acid, right? Remember in my second step, I was putting H3O plus to protonate. You can do that or water to do the protonation. Okay, but it goes to the least attitude now. Yeah, I'm going to explain you in a minute why does it go to the least attitude? Okay, so I didn't do the steps here. I forgot. This is not a full mechanism. Now it's a full mechanism, right? O minus attacks the H, proton transfer, and then the water leaves. Good. Okay, what happens in a non-symmetrical epoxide? In a non-symmetrical epoxide, we can attack it with another, a different nucleophile. Remember, it's a nucleophilic opening, so you need a nucleophile. Okay, so in this case, the potassium is silent. The SH is the one that does the attack. This SH, now the SH has two carbons to attack. It has to decide, where should I attack? Is it going to be again the tertiary? No. Why? Because remember, the tertiary was decided because of the O plus. The O plus was transferring the delta plus to the two carbons. But now, in this case, you don't have any plus. There is nothing here to transfer. So there is no delta plus here. So you cannot do it based on the delta pluses. So you're going to make it based on what? On hindrance. In the case of nucleophilic opening of epoxides, you will do it by the least hindrance. Okay? So which of the two carbons is less hindered? Of course, this one. So the nucleophile will attack to the least substituted carbon of the epoxide. So this one will go to here and this one by. Okay, you have electrons, but yeah. SH will add here. SH and the O minus will be pointing up. And the two methyls right there. After that, you guys add water. And that's your product, right? Your final product will be right there for the substitution, sorry, opening of epoxides. Okay, makes sense? Let me know you guys have any questions about this opening of epoxides. That's the mechanism. Do we need to know the mechanism for an opening of epoxide? Yes. Acid and nucleophilic? Yes. Acid-catalyzed and nucleophilic opening of epoxide, we need to know. Okay, so what else do we need to know? Epoxides, both acidic opening and nucleophilic opening. Okay, what else? For ethers, you need to know the Williamson ether synthesis. You need to know the synthesis of the ether in concentrated acid, right? For symmetrical ethers. What else? Cleavage of ethers. Yeah, but they're very similar. I mean, they're not really that difficult. They're all mostly SN2s, right? SN2s or SN, yeah, SN2. Right? These three are all SN2 reactions, so they are very, very, very similar, right? So those are the mechanisms that we need to remember. All right, so let's go back to the slides. Okay, that's the opening of epoxide for the nucleophile. Step 1 opens to the least substituted, and then in a second step gets protonated, right? So it gets protonated by the water. You can do it with all these nucleophiles. You see the nucleophiles right here. Sodium alkoxide, yes, that's a nucleophile. Sodium cyanide, cyanide is a nucleophile. There is no acid. There should be no traces of acid in this case. Okay, so Grignard can also be used for the opening of epoxides. The R group gets added. The SH, that's the example that I use. SH gets added to the least substituted. Cyanide, I did this one. LAH can also be used to open epoxides, but now you will be adding a hydrogen. Okay? That's how you have an epoxide. Always from the least substituted carbon. In this case, this one is symmetrical, so it doesn't really matter where it goes. But if you guys have a substituted epoxide like this one is a tertiary versus a primary, it can also apply to a tertiary versus secondary. Well, that one might be a little bit even, but secondary versus primary, yeah, that's another case of epoxide. Okay, good. That's a case for synthesis, starting material. Magnesium diethyl ether, you are adding right an alcohol. So you are, this one is one way, that's a synthesis problem. How to create an alcohol, right? A longer chain alcohol. You can do that with Grignard. With Grignard, you guys can add and get a terminal alcohol using a nucleophilic attack for epoxide, right? You have here, see, here the epoxide. If you want it in a more internal, then you use the Grignard, but you use the conventional, the right, the Grignard on an aldehyde or ketone. This one will never give you a primary alcohol, no, unless you use formaldehyde, right? But that's one way how to make primary alcohols with elongation, right? Primary elongation, a good way is to use the opening, nucleophilic opening of epoxides, and you can use epoxide, right? The epoxide as a starting material. Okay, so those are reactions involve, synthesis reactions involving epoxides. You guys, see how you do. I'll just skip this practice problem. Don't look at it. That's a summary of the, right? Summary of the reaction that we studied today. That's the summary also for the, right? The reactions in a more written way. This one is more schematic, right? How we can, I was using protonated alcohol and water, but you can also use HCl, HI, HBr in the acid-catalyzed opening of the epoxides, all right? NMR NMR we'll see from everywhere, but not that much in the quizzes or the exams. But in general, we are expected to remember, right? Expected to remember the reactions, right? The NMR. Okay, so I will have now at this point, I will do some synthesis problems. I have 6 synthesis problems that I prepared for you guys. You guys can stay for the next, for the first 2. You think that you had enough? I mean, you can cut this recording anytime. Okay, so they give me this problem. They give me this problem and they tell me how you synthesize this ether based on this, right, study material. Okay, ethers. How do I make an ether? Ether, I can make it from, alcohol with acid, right? H3O plus, the sulfuric acid. Another one is the Williamson ether synthesis. Those are the 2 ways how I can make ethers, right? These 2. But what I see is that I have on the left side, I have a 5-member ring. And here I have what? I have a 6-member ring with the oxygen. So what do I have to do with this cyclopentane? I need to find a way how to open this cyclopentane, because there is no way how I can just add 1 carbon or 1 oxygen just by putting it in, right? I cannot just insert it. No, I have to open the 5-member and they close it as a 6-member ring. So how do we open an alkene? Do you guys remember opening alkenes, breaking alkenes, cleaving alkenes? There is a reaction that is called ozonolysis, correct. O3 in DMS, I opened the cyclopentene. So now I will have 2 aldehydes. Okay, 5, 1, 2, 3, 4, 5. Okay. Now, all these reactions, they involve what? They involve alcohols. I don't have alcohols. What do I have? I have aldehydes. Can I reduce aldehydes to alcohols? Yes. How? With sodium borohydride, or you can use LAH, followed by water. That one, that's the previous chapter, alcohols, right? Preparation of alcohols. Professor, can you use sodium borohydride? Yes, you can also use sodium borohydride. Can I use LAH? Yeah, same thing. Doesn't matter. For aldehydes, doesn't matter. I reduce both and then I will get 2 alcohols. Now, what should I do? Can I make ethers from alcohols? Yes. Is this alcohol symmetrical? Yes, actually symmetrical. So can I use this method, alcohol in acid, to cyclize it? Yes. Can I use Williamson? No, you cannot use Williamson, because if you use Williamson, remember, you need 1 alcohol and 1 halide. You cannot just do 2, it's the same compound. If it's the same compound, you have to use the symmetrical, because this alcohol is symmetrical and your ether is also symmetrical. So it has to go through that reaction. So sulfuric acid concentrated, and it will give you the ether. Right? So the mechanism, we don't have to do the mechanism, but the idea is that the 1 OH gets protonated. Once the 1 OH is protonated, the second OH will attack intramolecularly. Okay, so cleave the alkene, get the aldehyde gets reduced by LAH, getting the two OHs, and the two OHs undergo the acid-catalyzed ether formation. Okay, good. You like this one? That's definitely is an ether. Once again, my ether can be made either by using sulfuric acid or by doing the Williamson ether synthesis, right? One of the two ways is to produce an ether. In this case, I have an unsymmetrical ether. So you have an asymmetrical ether, so definitely you cannot use the sulfuric acid. It has to be the Williamson ether synthesis. Okay, so what I remember from the Williamson ether synthesis is that the Williamson synthesis, it goes from an SN2 reaction. If it's an SN2 reaction, I have to look at my ether. Which one of the ether is, which one of the branches, right? The branches of the ether is better for SN2. This one. So this one has to be my halide. All right. What am I given? Oh, I'm given the cyclohexol. But I know the cyclohexol has to be the alkoxide. That doesn't agree. That doesn't make sense. They give me that as an halide, and here I actually need it as an alcohol. What should I do? Can I just, ignore it and then just do what I need to do? No. You have to follow the rules of the Williamson ether synthesis. The Williamson ether synthesis tells you that the least branch is for the halide and the most branch is for the alcohol. You have to follow that rule. You cannot just ignore it. So in this case, this one has to be the alcohol. So how can I make this one into an alcohol? Water in an SN1 reaction. Yeah. Okay, good. I make it into alcohol. Sodium hydride. Alkoxide. And after that, who? The halide. 2 carbons. And you get the product. Okay? Be very careful. Sometimes I might give you a particular study material that it does not apply or is not directly used. Because you might think like, oh, I have one half, I just need to add the other half. Not necessarily. If the rule goes against that, right? You have to switch them, then you have to correct that switch. I switched it, right? You see here in purpose, I switched it. I switched here the halide and the alcohol. I changed that in purpose. So what should you do? Well, adjust it. Can I adjust this? Yes. The halide can be easily converted into an alcohol with water. Professor, can I use OH? Yeah, but that one will give you actually more elimination. So the safest way would be to use water, SN1, because it will give you more alcohol. Less elimination, more substitution. But if you put OH and then write the correct product, I mean, that's okay. That's fine. You can just use OH or water. As long as you give me that intermediate, right? The cyclohexanol, this one. Okay. Okay, good. Clear. You see, this synthesis, I did it forward, but I had to do my retroanalysis. My retroanalysis was this part to determine which was my halide and which was my alcohol. That was the important part. That's how I knew how to work the forward side. All right. So great. So here, another one, another synthesis. Let's see this one. Alcohol and something else. Neighboring. Neighbors, OH, and a methyl. Okay. So anytime you guys see that a molecule gains 2 groups, one of them is an alcohol and one of them is something else, and they are both adjacent. So that's coming from an epoxide. Definitely it's coming from an epoxide. Right? Because remember, the epoxide is 2 things, right? So this is epoxide. You are adding something here, and the other side gets what? Gets the OH. So that unknown and the OH will be neighbors. So that's epoxide, chemistry of epoxides. So that's what we will do here. Let's make an epoxide. How can you make an epoxide, guys, from cyclohexane? To make an epoxide, I need an alkene. Do I have an alkene? No, I don't have an alkene. The only way how I can make epoxide is from an alkene. So I don't have an alkene. So let's make it. Br in light. Radical. Bromine. After that, sodium methoxide, or yeah, SN2 reaction. And that's it. That's all you guys need to make an alkene, okay? Bromine in light, or you can use MBS, that's okay. MBS also works. Or chlorine, that's okay. In this case, it works chlorine because there is all of them are secondary. So it doesn't matter, there's no selectivity. But just in case, yeah, use bromine. Okay, then after that, I do an elimination, an E2 reaction. Methoxide, I can use methoxide, terbutoxide, right? Terbutoxide works because I don't have Hoffman elimination here. They're all size F. Okay, after this, I use my NCPVA, metachloropyrbenzoic acid. Epoxide will form the from the epoxide. Epoxide. Professor, how do you know you're using wedge epoxide? Because the OH is wedge. The epoxide will preserve the OH will keep the same stereochemistry. Now, what am I adding? I'm adding a methyl. How can I add a methyl to an epoxide? Okay, you can add it using Grignard. Grignard is the only of the reactions. Let me see if I can pull it up from the right here. Grignard, see? The Grignard adds any group. This group can be methyl, ethyl, propyl, cyclohexyl, right? Anything, even phenol. Even phenol can also be added. Oh, I think you guys didn't see it. I saw it, but you didn't see it. My bad. This one, right? This Grignard. This Grignard, right? So adds the methyl, ethyl, propyl, cyclohexyl, even phenol can be added to this side, right? So in my case, I need to add a methyl. If you guys have to add a methyl, well, add a methyl Grignard. One followed by one. And that's it. That methyl will add here, right? No mechanism, right? So you only have to show the steps. This one is kind of picky. And then you might find this as one of the, questions is that this particular question or synthesis is telling you like, use this as your only organic compound. See, what is the difference with this? So here you could, let me see from the previous one. Right? For example, in our previous synthesis, right? So you guys were using water, inorganic, sodium hydride, inorganic, but you were using this ethyl bromide. That's organic, but you're allowed to use it, right? So it's not a problem. You're allowed to use it. You're allowed to bring it in for your synthesis, even though it's not given, but you're allowed to use it. So in this case, I use a Grignard. Grignard is also organometallic. It's organic. It's organic, inorganic at the same time, but it's organic. So there is no limitation. You can bring in organic molecules to your synthesis with no issue, no restriction. But if the problem tells you like this one is your only organic compound, then you are not allowed to bring anything else. Everything has to be made from this compound. Okay, let's see. So this one is an unsymmetrical ether. Unsymmetrical ethers are made by Williamson ether synthesis, right? We all agree with that? That unsymmetrical ether, the only way how we can make this guy is by doing the Williamson. The Williamson tells you that you have to do SN2. SN2 says that primary is better than secondary, better than tertiary. Okay, which one is primary? Primary here. This one is secondary. So the alkyl, the halide should be this side. And the alcohol should be this side. Okay? Yeah, we recall it, right? From the lecture, from what we just did. The least attituded side has to be the halide. And the most attituted side has to be the alcohol. Okay. Now I have to make that halide and that alcohol, both of them should be made from this compound. Okay. So what is my halide? My halide should be, that's the halide, and the alcohol should be this, right? 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, let's do it. How can I add a halogen terminal on an alkene? Anti-Markovnikov hydrohalogenation. Chapter 10 or chapter 8 as well. So you have this, I can add the bromide. That's that. Now, how can I have an alcohol Markovnikov? Oh, there are two ways, right? I can do oxymercuration, or in this case, I can use a simple acid-catalyzed hydration, H3O+. You use H3O+, it will give you this. This one gives you CCR, but here I have no risk of CCR, so you can do it. Okay, so now that I have it, this one is pre-treated with sodium hydride, right? I get the alkoxide, and then that's treated with the bromide. And the product is the molecule that was requested. And that's your synthesis. You have two paths, right? Two reactions. This one, you mix it, and this one gets transferred here to give you the product. Good. Great. I have the last set of synthesis, and then we're done for this chapter, relatively short. Okay, another epoxide. How do I know it's epoxide, professor? Because you have OH and OET. OH is one of the additions to my compound, and then the other one is trans, and you're adding something else, trans, right? Okay, so how do I know that it's epoxide? Okay, once again, maybe, okay, rewind. How do I know that this coming from a chemistry of epoxides? Because you have two groups added, adjacent. Two groups are adjacent, and one of them is OH. And they are trans. Okay, that's another thing that reinforces the idea that it is epoxide. Okay, I know that to make epoxide, I need an alkene. So how can I make an alkene from there? We did it before, right? Bromine in light. Bromine. After that, ethoxide. In an E2 reaction, I have the alkene, NCPBA. Okay. I have the epoxide. Now I have to do a epoxide opening. In this case, it doesn't matter if it's acid catalyzed or base or nucleophile, right? Or base catalyzed. Why? Because the epoxide is symmetrical. It's symmetrical, right? You see symmetrical, so there's no other substituents. So in this case, it doesn't matter. And also, it is the same branching, secondary, right? So it doesn't really matter if you guys have acid base or the nucleophile. So in this case, I'll just use the nucleophile. Sodium ethoxide followed by water. Can you use the acid? Yeah, you can also do the acid, no issue. You guys have to use the acid, so it would be methanol in acid, right? Methanol, because it's ethoxide in acid. It's the same thing. Because here it doesn't matter if you open it from the least attitude, or the most attitude, because they both have the same substitution. Yeah, that's it, the synthesis. Last one. After that, I'll let you guys go. Okay, another epoxide. How do I know? Because I have here a compound 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I'm adding an OH and a methyl again. Well, this methyl, because that's the trans methyl, right? Remember, this is a trans methyl. Okay, so they're adjacent, they are trans, and one of the things that I'm adding is an OH, so it's epoxide. Okay, let's do the epoxide. Once again, has to be made from alkenes. I don't have an alkene, I have to make it. Bromine light. Bromine light will add bromine to the most saturated carbon. This one is my most saturated carbon. I need to make an alkene. Where do I want to make the alkene? Do I want to make it size F or do I want to make it Hoffman? Think about it for 5 seconds. Correct. You want to make it size F. Why? Because the OH and the methyl are right here, right? Are attached to this, between these two carbons. So I want the double bond here. That double bond is size F. If it would be any of these two, it would be Hoffman because it's the least saturated alkene. I want the most saturated alkene, so I need to do the size F. Let's do it with ethoxide. Ethoxide is a size F base. Alkene there. Then epoxide, NCPBA. That's epoxide. So now I have to open it. Okay, so here actually I think there is a potential mistake because here there is a secondary versus, right? Sorry, tertiary versus primary, secondary. In this case, if I add the methyl will add from this side. Yeah, so maybe what I had to do is this one. Yeah, I made a mistake. That one will change things very much. Yeah, I made a mistake in this one. Yeah, I apologize. So it should be 2. Yeah, I don't know. You guys noticed the case. What happened is that I had to add the methyl to the most attituted, right? The most attituted carbon of the epoxide, which cannot be done, right? Because if I do a nucleophilic attack, I have to attack it from the least attituted, so which couldn't work. So that's why if I have this epoxide now, I can do easily the Grignard, CH3, MgBr, followed by water. So now the Grignard can add to any of the two, so either here or here, because it's kind of symmetrical. It will give you this product. Okay, before it didn't work because I added the methyl on the right position. It should have been to the least attitude, not to the most attitude. All right. Okay, so that's it. I mean, that's all we have for chapter the epoxides, right? Make sure that you guys remember about the crown ethers, right? The application, and also the sharpless epoxidation. Those are very, good topics for us to remember, okay, for this particular chapter. Okay, so remember to let me know you guys have any questions. I'm available by email or by office hours and during lab hours. Okay, bye bye. See you for the next chapter.